A'udhu billahi minash shaitani rajim. Bismillahir Rahmanir Rahim. Assalamu alaikum dear fellows. My name is Muhammad Rafeel. I am the student of BS Mathematics 7th. Today the topic of my presentation is from the course of Functional Analysis 1, course code Math 324, Department Institute of Numerical Sciences Cust Cohort. The outlines of my presentation is first introduction to Hahn-Banach Theorem, and then second proof of Hahn-Banach Theorem for norm spaces and their consequences. Later at the end there will be references. Introduction. The Hahn-Banach Theorem is an extension for linear functionals. The object to be extended in this theorem is a linear functional which is defined on a subspace Z of a vector space X. So actually this theorem provides an extension of linear functional, that is, when a subset of a vector space is given, then under certain condition it provides an extension. Before going to prove the Hahn-Banach theorem for norm spaces, we will define some basic terminologies which will be frequently used in the proof of the Hahn-Banach theorem for norm spaces, in which first is linear extension of a functional, second sublinear functional, and the third Hahn-Banach theorem in generalized form. First, what is linear extension of a functional? Let f be a functional defined on a subset Z of a vector space X. A functional f tilde from X to R is said to be an extension of f from Z to X, that is, from subset to a vector space X. F tilde of X is equal to f of X for every X belong to Z. Remember two things for the linear extension of a functional. First, it will be defined on a vector space X. Secondly, the linear extension f tilde, which is defined on a whole space X. If we find the images of f tilde on X, it will be equal to the images of f on X. Here is an example. Let A is equal to 1, 2, which is the subset of R, and f from A to R be defined as f of 1 is equal to 1 and f of 2 is equal to 4. We will find the extension of f. Then f tilde from R to R defined as f tilde of X is equal to X square. So this is an extension of f. This f tilde is an extension of f. Now we will check the two properties of linear extension. First, you see the f tilde is defined on R. Secondly, if we find f tilde on 1, and then it is equal to 1, which is the same as f of 1, and second, f tilde of 2 is equal to 4, which is equal to f of 2. The two properties of linear extension is satisfied. So f tilde of X is equal to X square is linear extension of f. Here question arises, is all functional defined on R will be the linear extension of f? The answer is no. Here is an example. Here you see g from R to R defined by g of X is equal to X square. Here g of X is defined on R, but still it is not the linear extension of f, because if we find the value of g on 2, which is equal to 2, and the value of f on 2 is equal to 4, which is not equal to 2, so g is not linear extension of f. Now sublinear functional. What is sublinear functional? Sublinear functional is a real valued functional p from X to R, where X is any vector space which satisfies the following conditions. First, it will be subadditive, that is p of x plus y is less than or equal to p of x plus p of y for all x y belong to x. Second, p positive homogeneous, that is p of alpha x is equal to alpha p of x for every alpha, for alpha greater than or equal to 0 and r and x belong to x. Remember three things for sublinear functional. First, it will be real valued, and second, it will be subadditive, and the third, it will be positive homogeneous. Here we didn't use the absolute because here alpha the vector space is real. If the vector space is complex, then after some modification we can define alpha. Here is an interesting example: norm function which from x to r, which is sublinear functional because it satisfies the three properties of sublinear functional. First, it is real valued, and second, it is subadditive. Here x plus y, length of x plus y is less than or equal to length of x plus length of y, and second, the length of alpha x is equal to absolute into length of x plus which is equal to alpha into x absolute x norm. But it is not linear because of the property n4 of norm. Now the Hahn-Banach theorem in generalized form, which we will use in the proof of Hahn-Banach theorem for non-spaces. Statement: let x be a real or complex vector spaces and p a real valued functional on x which is subadditive, that is for all x y belong to x, p of x plus y is equal to p of x plus p of y, and p of alpha x is equal to absolute of alpha absolute into p of x. Furthermore, let f be a linear functional which is defined on a subspace Z of of x and satisfies the absolute of f of x is less than or equal to p of x, that is p of x, that is the given linear functional is bounded above by p of x. For Hahn-Banach theorem in generalized form, we need two things. First, we will find a real valued functional which will be subadditive and defined on the vector space x, and second, we need a linear functional which will be defined on x, and also it will be bounded above by p of x, which is subadditive, which is a sublinear functional. Then the Hahn-Banach theorem guaranteed that there will be a linear extension from z to x satisfying f tilde of x absolute is less than or equal to p of x, that is the linear extension will also be bounded above by p of x for all x y, for all x belong to x. Now I come to the main topic of my presentation, which is Hahn-Banach theorem for norm spaces. Let f be a bounded linear functional on a subspace Z of a norm space X. Here f is not only a bounded linear functional, but it is also a bounded linear functional which is defined on a subspace Z. Then there exists a bounded linear functional f tilde on x which is an extension of f to x and has the same length, that is the length of f on its domain is equal to the length of f tilde on its domain. This is very interesting because you see that we have a norm space X and at subspace Z and a linear function, a bounded linear functional which is defined on this Z. Theorem says that corresponding to each linear functional, bounded linear functional, there must exist a bounded linear extension. More interestingly, if we imagine that the domain of f is less than the domain of f tilde, that is the domain of f is subspace Z and the domain of f tilde is a whole vector space, but surprisingly the length of f on its domain is equal to the length of f tilde on its domain, which is a vector space X. So this is an amazing extension in which the length does not disturb. To prove this theorem, we need a sublinear functional, and how it will be created, let's see. From the definition of p of x, the absolute of f of x is less than p of x, and also this p of x is a sublinear functional. So we use generalized Hahn-Banach theorem, which says that there exists a linear extension. There exists a linear extension f tilde from x to k, such that this f tilde of x will be equal to f of x for all x belong to z. And second, this f tilde will be bounded above by the sublinear functional p of x. So these are the two outcomes of the generalized Hahn-Banach theorem, which says that there exists a bounded linear extension. There exists a bounded linear extension f tilde, which is the value of f tilde on x and the value of f on x will be same, and this linear extension will also bounded above by this sublinear functional p of x. So here absolute of f tilde of x is less than or equal to p of x. The value of p of x is here, and if we take the supremum of x belong to x for all non-zero vectors, then this the ratio of f tilde on x over the norm of x will be less than or equal to the supremum of f of the length of f on z. And on the right hand side, f of the length of f on z is positive, so there is no need of supremum. So f tilde, the norm of f tilde on x is less than the norm of f on z. Since under an extension the norm cannot decreases, we also have the norm of f tilde on x which are greater than or equal to the norm of f on z. So from this and this, this implies that the length of f on x is equal to the length of f tilde on x is equal to the length of f on z. So this completes the proof. So the main theme of this theorem, that is the Hahn-Banach theorem for norm spaces, is that if we have a linear functional defined on a subspace Z of a vector space X, then there must exist a linear extension of this f such that the length of this linear extension, that is f tilde on x, will be equal to the length of f on z. Now we will prove some important consequences, that is some important application of the Hahn-Banach theorem for norm spaces, in which corollary number 1 is the bounded linear functionals. Let X be a norm space and x0 is equal to 0 be any element of X. Then there exists a bounded linear functional f tilde on X such that the length of this f tilde is equal to 1 and the value of f tilde on x0 is equal to the length of x0. This is very interesting corollary. This corollary says that corresponding to each non-zero vector of X, there exists a bounded linear extension f tilde on X such that the length of this f tilde will be equal to 1 and the value of this f tilde on x0 will be equal to the length of x0. And to prove this corollary using Hahn-Banach theorem for non-spaces, we need two things. First we need a subspace or subset Z, and second we need a bounded linear functional which is defined on this Z. And here we are given just one vector, and you will see that how we create a subspace using this only one vector, and how we find a bounded linear functional. So take proof. Take Z is equal to span of X, that is Z is equal to alpha of x0 such that alpha belong to K. This is a spanning set, so Z is equal to the spanning set of x0. Spanning set contain all the linear combinations of x0. Let X be any arbitrary point in this Z. Define f from Z to K by f of x is equal to alpha of x0, because x belong to this set, so it can be written we can write it alpha x0. If we apply this f on alpha x0, it will give alpha into the length of x0. Now we will show that this f is bounded linear functional. First we will prove that it is linear, later we will prove that it is bounded above. Now first property of the linear functional is, if we apply f of f on x plus y, that is f of f x0 plus beta x0. Here x and y belong to this spanning set Z, so x x is equal to alpha of x0 and y is equal to beta x0. Using the property of vector spaces, alpha plus beta into x0. If we apply this alpha f on this vector, then alpha plus beta come outside into the length of x0. Here if we apply this in the length of fx0 on alpha and beta, we get alpha into length of x0 plus beta into the length of x0. So first condition of linear functional is satisfied. Now we will see the second condition of this theorem, of linear functional. So we take a scalar multiple of x which is equal to v alpha of x0, because x is equal to alpha x0. If this f act on this, so the v alpha come outside into and x0 become the length of x0. So as alpha into length of x0 is equal to f of x, so alpha v of x is equal to v alpha of x. So the two conditions of linear function are satisfied. Now we will prove that this alpha of x is bounded. So f of x is equal, here f of x is equal to alpha length of x naught. Take absolute on both sides. Absolute of f of x is equal to alpha into norm of x naught absolute. So the absolute of alpha into length of x naught. Here we use the property of norm, that is we can combine alpha and x naught, and alpha x naught is equal to x. So f of x is equal to the length of x. As length of x is positive number, so we can take it to the left side. So the absolute of f of x over the norm x is equal to 1. If we take supremum, then it will still equal to 1, as 1 is finite. So the length, f of x is bounded. Hence f tilde from z to k is a bounded linear functional. F from z to k is bounded linear functional. Using Hahn-Banach theorem for norm spaces, there exists an extension f tilde from x to k of f such that f for all x belong to z, f tilde of x is equal to f of x. Here if we apply f tilde on x naught, then it will be equal to f tilde into f tilde of 1 into x naught. Here we can write x naught is equal to 1 into x naught. If we apply f tilde on 1 into x naught, it will the 1 will come outside, and the x naught become its length. So f tilde of x is equal to the length of x naught. So first property is satisfied, that is f tilde of x is equal to the length of x naught. Secondly, we prove that the length of f tilde on its vector space x is equal to 1. Using Hahn-Banach theorem for norm spaces, the length of f tilde on x is equal to the length of f on z, as the length of f on z is equal to 1. So this implies that the length of f tilde on x is equal to 1. Corollary number 2: non-zero norm and non-zero vector. For every x and norm space x, we have the length of x can be expressed as the supremum of absolute of f of x over the length of f. Here the supremum is taken over all bounded linear functional. Proof: from the corollary number 1, which says that for every non-zero vector in a vector space, there exists a bounded linear functional f tilde on x such that if we find the value of this f tilde on x, it will be the length of this x, and the length of f tilde will be equal to 1. Hence supremum of this ratio, that is the absolute of f of x over the length of f. Here the supremum is taken over all the bounded linear functional, so it must be greater than or equal to the absolute of f tilde of x over the length of f. Here f is only one bounded linear functional, and this is the set of all bounded linear functional. Here we are given that the absolute of f tilde of x is equal to the length of x, and the length of this f tilde is equal to 1. So the length of x tilde, and so the length of x is smaller than the supremum of this ratio. Also, using the property of bounded linear functional, the absolute of f of x is less than or equal to the length of f and into the length of x, and the length if we take the length of this f is non-zero, then we can take it to the left side. So the absolute of f of x over the length of f is less than or equal to the length of x. If we take the supremum to both sides, here the length of x is positive, so there is no need of supremum. So the supremum of f absolute of f of x over length of f is less than or equal to the length of x. Hence from equation 0.5 and equation 0.6 we have the length of x can be expressed as a supremum of f of x absolute over the length of x, and hence we are done. Now the last corollary which says that f of x naught is such that f of x naught is equal to 0 for all f belong to x dash. This x dash is the set of all linear functional, then x naught is equal to 0. That is, if all the linear functionals apply on this x naught and this x naught and it gives the and it is equal to 0, then this vector itself equal to 0. We can easily prove that using the previous corollary from the equation 0.4 of the previous corollary. Length of f x naught is equal to supremum of f of x naught absolute over the length of f, and here we see that the value of f of x naught is equal to 0. So f of x naught is equal to 0 and the absolute of 0 is also equal to 0. So the supremum of 0 over the length of f. So the length of x naught is equal to 0. If the length of x naught is equal to 0, then the vector x itself equal to 0, and hence we are done. And at last, there are references. All the materials here are taken from these references, and if you have any question, you can ask in comment section. Thank you so much.